Today, linearization and Newton's method. So these are the first of a huge group of computational methods that we're going to learn. And essentially, what I'm asking you to do here is estimate some irrational numbers. Square root of 105, the natural log of 3, sine of 1. Right, I don't know what the sine of 1 is because 1 is not one of the radian measures on the unit circle. So, but could I get something close? Right, I can probably think of a good way to estimate square root of 105. You probably have a good idea how to do that. You could estimate ln3 easily if you think about the fact that you know what the ln of E is, and E is 2.718, which is pretty close to 3. You could estimate sine of 1 by thinking, I don't know what the sine of 1 is, but you know what? What's really close to 1? What's really close to 1 that is on the unit circle? Pi over 3. Because pi is a little more than 3, so 3 over 3 is going to be a little bit more than 1. So take a moment to estimate what you think those should be. All right, so I hope in your estimates you took into consideration, for example, that square root of 105 should be more than 10. All right, ln of 3, because ln is an increasing function, ln of 3 should be more than 1. And sine of 1, since sine is an increasing function, should be a little bit more than the square root 3 over 2. All right, so let's think about some of those estimates. So since I know that, like one way I can think of it is the square root of 105 is close to the square root of 100, which is 10. All right, and I know that square root is an increasing function. 105 is more than 100, so my guess might be, I don't know, I guessed 10.2. Your exact guess, we're just guessing at this point. For ln of 3, I can say ln of 3 is approximately equal to the ln of E, which is 1. All right, so, and E, actually, yeah, 3 is more than E. Ln is an increasing function. So I don't know, but 3 is, like 0.3 more than 2.718. So I don't know, maybe it's like 1.3? These are my guesses. I don't know what your guesses were. Sine of 1, we know that it's going to be close to the sine of pi over 3, which is equal to square root 3 over 2. And I don't know how to say a little bit more than square root 3 over 2. So you know what I'll say? I'll say square root of 3 over 2 is itself approximately equal to about 0.866. Pi over 3 is, again, a little bit more than 1. All right, so 1 is a little less than pi over 3, and sine is an increasing function, right? 105 was more than 100, so we estimated more. 3 was more than E, so we estimated more. 1 is a little bit less than pi over 3, so I don't know. What do you like here? Like 0.84 maybe? 0.84 might be a good guess. All right, so this is guesswork. Why are we guessing when we're mathematicians? Here's why. What you're really looking for is, for another way to look at the question is, why don't I just do it on my calculator? I paid $100 for the thing. If I want to know what the square root of 105 is, why don't I just go square root of 105? Oh, why don't I turn it on first? That's why. All this stuff worked out. Where is it the square root of 105? All right, it's 10.24. Hey, it's pretty close. That was just a guess too. 10.24. But what we're going to see is how I could get a better estimate. But here's why we study numerical methods. So sometimes computational methods, sometimes numerical methods, sometimes called finite elements, things like that. There are ways of coming up with values for a square root of 105 without a calculator. Well, why would you do that? It comes down to this. How does the calculator know what the square root of 105 is? All right, I guessed that the ln of 3 was 1.3 using my knowledge of the function ln of ln and one function I knew. But what is the ln of 3? It's 1.098, and I'm very confident that my calculator has the correct answer. Why? How did it do it? How does the calculator do it? So the numerical methods that we're going to be talking about are primarily of interest to programmers. So people who work for TI and program the calculators, or people who work for Mathematica or Google or somebody who writes mathematical software, all right, they want algorithms to know how you compute something like ln of 3, all right? What your calculator does not have is like a table of values, because otherwise to get, you know, if you wanted the ln of 2.71859, all right, you don't want to store a huge, every possible ln in your calculator as a value, because that would take up too much memory. So what you need, and you see how quickly the calculator came up with this, what you need is an algorithm that approximates these values very quickly. Now, every value that your calculator has given you here is an approximation. Not one answer is exact. The reason is these numbers are all irrational numbers. There is no expression in decimals that exactly corresponds to the square root of 105. Square root of 105 has infinitely many decimals and they never repeat. So any decimal you write down is an approximation. The trick is, can you get an approximation to 10 decimal places or 20 decimal places in a fraction of a second? That's what these computational methods are about. The first computational method we're going to look at is called linearization. You're going to see it's actually a very crude idea, but it gives some pretty good estimates. What you want to keep in mind as we go into linearization is that it is only the first baby step into the world of computational methods. So we're going to see much more sophisticated methods as we go along. Newton's method, in fact, is more sophisticated than linearization and gets more accurate results. We're going to see, but the best ones that we're going to see are Taylor polynomials, and that comes at the end of the course, because you have to do a lot of stuff first, okay? But linearization, by the way, is a form of what we're going to study at the very end of the year called Taylor polynomials. And I'll talk a little bit about that. So you want to think we're looking at ways to compute values of functions. They are computational methods, or sometimes called numerical methods. And these first ones are going to be very crude. But there's a whole field of algorithms that are used to compute these values. They are the engines behind everything a calculator does, or Desmos does, or Mathematica, or Wolfram Alpha. Any of those computational engines has these things, these methods lurking in the background somewhere. So we will look at those in detail next.